The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. This is Christine Perret. Thank you for joining me for this special Area Research Committee webinar on May 22nd. It's a pleasure to have with us today Dr. Steve Feiner, and I'm going to ask everybody to hold their questions until the end of the webinar. There will be time for questions. You can use the chat feature in your GoToWebinar control panel if you think of anything you'd like to have discussed at the end of the presentation. And I want to thank Steve Feiner for his time and preparation and in delivering this special webinar. Thank you so much for sharing with us, Steve. Over to you.
You're very welcome, Christine. It is a pleasure indeed to be here. This, of course, may well fall prey to the variety of sins that befall people trying to do conferences like this remotely. I have, I think, pretty good upload and download right now, but we'll see what happens. Let me tell you a little bit about myself. I'm a professor of computer science at Columbia University. I've been doing AR and VR research for just a couple of months shy of 30 years at this point. We've been particularly interested in skilled task performance, and I will talk a bit about some of the work that we've done on user interfaces for enterprise AR and VR. At a high level, we are interested in user interfaces for AR and VR in general. We've been doing a variety of work over the past several decades, a couple of images from some of which I'm showing you here. Work on navigation, helping people be able to find their way around both indoors and outdoors. And on the left, you're seeing a backpack system that's using a real-time kinematic GNSS system that we're coupling together with the SLAM from HoloLens to enable people to get a centimeter level accurate tracking and a 10 hertz update rate as they walk around outside on our campus. We're also interested in AR and VR visualization. I will talk a bit about the project that the center image is about. And one thing that's been of great interest to us for literally the entire time we've been doing AR and VR is task assistance. So I'm going to lead by talking about some of the work that we're doing on using AR and VR to assist people in performing skilled tasks. So in general, effective user interfaces is the issue that we try to address in my lab. And we're looking at ways in which AR and VR can help people accomplish whatever goals they have more effectively, whether working by themselves or together with others, whether they, when together, are co-located or remote and distant. First domain I'm going to address is remote task assistance. This is that very familiar notion of a local technician who is boots on the ground actually performing some skilled task, and the idea of a remote SME or subject matter expert who is going to be advising them and hopefully in a way that can be every bit as effective as if you actually flew that remote SME to the location where the technician actually is. So what we're trying to do is to come up with ways of being able to interact with AR and VR that make it unnecessary to have that person with expertise be physically co-located with the person who needs assistance. So I'll talk a little bit about some of the work that we've done. There's two things that we've tried to address in our lab. One of them is helping the technician get in place, get to the right place, the right position, the right orientation to perform a task. We can think of this as the where. And the other complementary issue is how, helping the technician actually perform whatever task it is they need to perform. So I'll tell you a little bit about some of the work we've done on getting in place, and I'll begin with some stuff that's a little bit old, and then you'll see why I've talked about it and what we've been doing since then to try to do better than it. In the work that I'm going to talk about now, you're seeing a still image of a desktop environment. You see a kind of white gloved hand coming in from the lower right. And that is being seen at full scale. It's literally the tracked hand of the remote expert. And they're interacting with a scale model, not much bigger than hand size of a aircraft turboprop engine that we happen to have in our lab. And the idea is to allow this remote expert to specify a location and orientation that they'd like to have the technician be at. And in fact, in this work, you can see a little sphere with a pyramid sticking off of it to the left. And that, in fact, is a representation, live track representation of the head of the technician so that the SME can see where the technician is and where they're looking roughly as they try to direct them to the place they want them to be. So how do we actually do this direction? What you're now seeing is a view through the video see-through AR head-worn display of the technician in this work. This work was done 5 or 6 years ago. And in fact, you're seeing through one eye of a Canon HMA1 video see-through head-worn display that we were using back then. The stuff off to the left is the actual Rolls-Royce Dart 510 engine that we have in our lab. And the thing on the right is a virtual kind of picture frame that's going to be put in the environment of the technician that will let them see where they're supposed to go. So let me show you what this actually looks like live. In the interest of trying to conserve bandwidth on all ends and make the best use of it, I'm going to make the image be a lot smaller. I'm going to play you some video right now and hope this comes across well on your end. So here you're seeing a third-party view of our remote expert. They are spinning this little lazy Susan in front of them that has that little scale model of the engine. All those things sticking out of it, kind of like cloves sticking out of an orange, are representations of different viewpoints that the technician can be at. Our expert is selecting one, and now you see our technician wearing the HMA1 moving into place. And the way they do that and know where to go is what you're seeing now, which is this representation of this kind of splayed picture frame window. And as the technician now looks through it, we can see the expert pointing with this long kind of Pinocchio nose pointer sticking off their finger, enabling them to more easily point at a portion of this engine. So this is the work that we did back around 6 years ago in trying to get people to the right place. And the problem we had with this is that if we put this kind of picture frame in someone's environment, different people interact differently with it. There's some people who will walk right up to it and stick their head through it. And there are other people who treat it a little bit more like, let's say, the picture frame surrounding a picture in a museum. And we know that if we get too close to the picture, the guard yells at us. And so there's some people who will basically keep a respectable distance, and they think they're looking through it, but they're really backed off a bit. And there are many tasks in which we don't want to have that kind of indecisiveness about where the person is going to be. And we tried to come up with a way of being able to better and more clearly indicate where we wanted you to be, how we wanted you to be oriented, without necessarily confining a person to having to be at a very specific place and looking in a very specific direction. Because indeed, there are many tasks in which you can have a variety of different locations and a variety of different orientations. While, of course, there are also tasks like looking through a microscope where you're very, very constrained. So we wanted to be able to come up with a way of representing effectively to people the constraints on position and orientation. So let me show you what this looks like. The work that we then did is something that we call a parafrustum. And the image that I hope you're seeing right now looks kind of like an airbag in the process of being deployed. And it is actually a target. And the user, an example of whom you see on the left over there, their task is, when they see this, to essentially stick their head inside of it. So this is, in our work over here, represented as an ellipsoid. And the size and the orientation and the position of that ellipsoid determines where the head needs to be. If it's a very small ellipsoid, you're very constrained. If it's a very big ellipsoid, there's a lot of good places you can be. And so this is letting us specify where we want you to be and the amount of slop you have in getting there. Now, in addition to getting you positioned, we want you to be properly oriented. And so it turns out that this thing, that's airbag-like thing, we call the head volume, because that's where your head needs to go. And there's another ellipsoid, which we call the tail volume. And that actually is going to be used when you put your head inside to help you orient yourself correctly. And so our representation of position and orientation is actually a pair of ellipsoids, and they're actually wrapped in a convex hull. Think about wrapping them as tightly as you can with kind of like a rubber wrapper around them. And that convex hull, in fact, is represented with a set of ribs, these light bluish ribs that you're seeing connecting the two ellipsoids. So I'm going to show you a couple of still images, and then I'm going to play you a video. It's going to go by pretty quickly, and so I wanted to use the stills to explain what's going on. And so at the upper left, you're seeing an example of another version of a head and tail volume here. The head is very small. The tail is actually fairly big. And we're seeing this from one eye of the technician. The technician is now moving in to get their head inside of that yellow ellipsoid. When they get their head inside, within a couple of fraction of a second pretty much, they're going to see these blue ribs around the outside start to disappear. As long as this very thin red line, which represents that tail volume, is inside of their field of view and not blocked on any side of it. Now, if the user sticks their head too far into that ellipsoid, then you're going to see what's happening at the lower left over here. That very thin red line starts becoming kind of a very angry red. And in this case over here, it's even angrier and angrier. This is an example of what happens when you don't pay attention to being told to back off. And in fact, we're now cutting off the top and the right-hand side of that red tail volume. And if only one of the right or left is cut off, or only one of the top or bottom, that's bad. And so if the ellipsoid is too big to be able to fit in horizontally, that's okay as long as you're cut on the left and right. If it's too big to fit in vertically, as long as you're cut on the top and bottom, that's okay. But if it's only cut on the right and not the left, or the bottom or top and not the other side, you have to reorient yourself to make it fit. And then finally, at the lower right-hand corner, you can see that that ellipsoid fits perfectly. And there's actually a range of angles we can be at, positions we can be at, and still have that ellipsoid fit. And that, in fact, is the range that corresponds to the good positions and orientations that our user can be in. So let me show you what this looks like when we actually run it live. I will go back to making this small again, and we'll go to the next screen. And now you're seeing live view through one eye in the head-worn display. As we get our head inside, that yellow film disappears. The ribs are now gone. Everything's good, but we're sticking our head way too far. That red thing is getting really big and angry. And then we're just showing the example of what happens as you cut it on just one of the top or bottom or left or right. And now if we move back in, now everything is good. And the range we're seeing as we move around, this corresponds for that particular perifrostum to the good positions and orientations to be in. So this is basically designed for a task in which we can figure out the good places for you to be to get you into one of those good places without having to constrain you to be in only one of them. So this is some of the work we've done on getting you to the right place. Now I'll talk a little bit about actually getting you to perform the task. So I'm going to show you some imagery from a demo that we did at the SIGGRAPH conference back in 2017. And on the left, we're seeing a view through the head-worn display of our local technician working in augmented reality. They're looking at the actual task domain. On the right, we're seeing our remote SME and what they see in virtual reality. And in this work, we're specifically interested not only in having our remote SME be able to do things in AR, but in the situations in which our remote SME might not actually have a interesting task domain right in front of them to work with, they may want to do everything virtually. And as we'll see, part of what we're trying to do over here is make it possible for that remote SME to be able to do things, for example, from home rather than from work. And the reason we want that is a person gets to be a SME through experience. Experience takes time, and there are many situations in which you might have somebody who has literally been with the company for decades. They've gotten really good at a whole bunch of stuff. They know pretty much everything there is to know about a whole bunch of products. And of course, around that time, they may be in a situation in which they're thinking, well, you know, I've spent a lot of time working, I have grandkids, I like to spend some time with them. Maybe it's time to retire. And that may be a situation in which there's literally nothing you can say to them, no amount of money within reason you can give them that's going to make them say, yeah, I guess I am willing to stay at work. And so we can imagine a situation in which, when the technology is right, someone who wants to retire can, you know, have the retirement party and leave, but perhaps you could say to them, are you willing to work from home? To do this essentially whenever you want to, just give us a little bit of advance notice. No need to come into work. No need to have messy, disgusting, greasy equipment at home to work with. Everything will be virtual. You'll do it with a VR system. Oh, you don't have a VR system? Buy you one. Your grandkids can play with it when you're not using it. And now you get to, whenever you want to, within reason, be able to go and assist people, work with your colleagues who maybe you do sort of miss. You might not miss seeing them 40 hours or 50 or 60 hours a week, but you know, you've made friends over the years, and the idea of being able to also help train young people who you've trained before, and now you're not going to get to do that if you're completely retired, that's a good thing. And I watched people like my father, for example, retire and then essentially rot because he was not doing all the things he said he was going to do in his retirement, and he wasn't getting challenged the way that he used to be challenged when he was at work. So I think this idea of having AR and VR make it possible for somebody who has a lot of knowledge to still be able to use that knowledge in a way in which they don't feel like they have to do it 40 hours a week and they have to go and brave the rush hour traffic in and out can be positive. So having said that, let's see what this thing looks like. I'm going to show you basically some scenes from a demo that we did that was designed to be used by attendees at a conference, people who we had promised when our demo was accepted. We would take no more than around 5 minutes to have a person put on a head-worn display, learn about how to use the system, actually use the system, complete a task, take the head-worn display off and be done. And again, all that within 5 minutes. And so the task domain had to be really simple. In this case, we have a very simple chassis that we made. It has a bunch of optical mocap markers on it that enable it to be tracked in 6 degrees of freedom. That means we can pick it up and the system knows its position and orientation. We have a set of gears and axles. The gears that are tracked are off on the right side. The axles, there are more of them than there are gears, are on that chassis. And we're imagining a situation in which we have someone who knows how to put gears on axles. They just don't know at a certain point which gear goes on which axle. And so our remote expert is going to analyze the situation and need to tell them what to do. So here we see a third-party view of our local technician. They are working in this case with a Meta 2 optical see-through head-worn display. This is a relatively wide field of view stereoscopic head-worn display. It's tracked in this case with this optical mocap technology along with the task domain objects. So everything that is physically being done with the task objects by this technician can be seen by the remote expert. Here is our remote expert. They, in this case, are wearing a Oculus Rift. And they are interacting with a virtual copy, a live virtual copy of the technician's task environment. You can think of it basically as being a digital twin. And now our SME is going to get to demonstrate the task to the technician. They're doing it in VR. Ultimately, I think, AR probably makes more sense even if you don't have the task domain at home. You may have that glass of beer, or the dog may be running around, and you want to have some situational awareness. But for this demo, it was easiest and clearest to explain to people to simply really make it pure VR rather than AR. So what does our SME see? Here you're seeing CAD of the individual components that are being manipulated by the technician. And we call these virtual proxies. We'd like to have the SME reach out and be able to grab those virtual proxies that they want to manipulate. But the problem, of course, is that if the virtual proxies are really being controlled by the technician because they're slavishly doing what the technician is doing with the real parts, we don't want to have the SME and the technician fighting over the virtual copy. And so what happens is when our SME reaches out, in this case with an Oculus Rift controller, to grab, say, a virtual copy of a gear, what they get actually is what we call a virtual replica. They automatically create their own copy of that gear that they can control and that the technician can also see. So now the technician sees the virtual copy, the virtual replica, being manipulated by the remote SME. They can hear the remote SME talking to them. They can have a conversation that isn't just looking, or rather listening to someone, isn't just looking at a video of them, but they're actually seeing them manipulate stuff in 3D in the technician's own environment. So in this way, this differs greatly from a lot of the remote sort of FaceTime-like things that people have done in this general domain, because there are tasks in which simply seeing a live video or canned video of someone doing something isn't enough. The tasks may be sufficiently 3D and interactive that you really need to see the person performing them in your own environment. Now, by the way, one of the things you're going to see are these sort of rubber band lines that are going to be used to connect, say, a gear to an axle. And one of the things that's happening in this demo is we had the ability for people who are simply conference attendees to walk up and be able to play the role of a technician, but also be able to play the role of the SME. Now, of course, none of our people playing the role of a SME, except for us, really knew what they were doing. And so in order to make the demo work from the standpoint of the SME, we had to sort of have a meta SME built into the system. And so those rubber band lines that a real SME would not need are going to be seen by the SME as well, so they can know what to do and be able to correct the technician and compliment the technician when they do stuff right, even though they really are just another person who doesn't know what they're doing, who's walked up and been shown how to use our system. So let me show you what it looks like from the standpoint of the technician. So we're going to look at a view through an RGB camera that's actually in the Meta 2 head-worn display, not unlike the RGB camera in, say, a HoloLens. And when I start this playing, and I have to remember to make the video a little bit smaller so that this works, you will see these ghostly versions of the gear moving around because they're being moved by the remote SME. So that gear moving into place is being moved by the SME. Our technician now picks up their own, moves it in, following that little leader line. We assume they know how to put gears on axles. And it's a square hole, it's a square cross-sectional gear, and that's one of the things we actually had to tell people during the demo. So here our technician puts it in place, and it is now in place. And having done that, if they got the wrong order or anything, if they pick them up, you can see they're still connected by those rubber band lines, showing them which things go where. And in fact, as they put them in place, you'll see that ghost version kind of disappears. And in many ways, you could actually argue this is better than if you had the SME right next to you. Because if the SME right next to you put their own copy, physical copy of the gear on the axle, for you to then do it, they'd have to pull their gear off. And in this case, you can still see their virtual gear right where it belongs, and only as you move in close enough does their virtual gear disappear, so your gear can your physical gear can take over. So let's now see what it looks like from the standpoint, excuse me, of our SME. And so now we're seeing the SME's view in VR. And now when I start this, you're going to see essentially what the SME is seeing. And as I said, this is not really a SME. This is someone who's being shown as well how to show the technician what to do. And so in this case, our SME is controlling these virtual proxies. When they reach out and grab something, they're actually cloning it. So now we see the clone copy in their hands. They put it on the axle. And in fact, instead of them having to really put it right correctly in the axle, when they get close enough, it just spins into place, because that's not the point. The technician knows how to put things on axles. The point is which thing goes on which axle. Let's not waste the time of the SME by having them try to put a virtual cross thing with a square cross section on a cross section axle. That doesn't make any sense. And so now our technician is having to put the real thing on, and so you can see them just manage to now get it in place, and now they're done. So this is an example of the kind of thing that we're doing in trying to allow our remote expert to be able to really show things happening in 3D, in this case with CAD models, tracked CAD models, of all the important things that are in the technician's environment. So now I'm going to switch to a very different domain. This is also collaborative. It's an example of urban visualization. And the image that I'm showing you over here might look a bit familiar. If you're looking at this and say, that's New York, you're kind of sort of right. This is actually not Manhattan. It is, in fact, a model of Manhattan, a physical model of Manhattan, one that was built in the early 60s for the 1964 World's Fair, New York City Pavilion. This was put together with quite a lot of money. And in fact, every single building in the entire city, all 5 boroughs, was actually modeled to make this physical model. Every building is actually in there. This thing costs millions of dollars, and it is in fact nearly 100 feet on a side. It is still to this day the world's largest physical scale model of any city. And while arguably it was built to be a New York World's Fair exhibit, it was designed so that after the fair was over, it could be used to do urban planning, urban design, put together by Robert Moses, who directed the fair and had the money to spend on this. And the idea was that a urban planner might be able to sit with others, or stand with others rather, aim their flashlight, because they didn't have laser pointers back then, and say, should we put the bridge over here? And see this in context of literally this fully detailed model of the city. So that was then. Computers back then simply were not doing this kind of graphics. But we can now do this with not the high-end machines that we would have done this with, say, 5 or 10 years ago, but with things that are literally within the reach of a teenager. But which also can be, of course, used by people trying to accomplish real tasks. So one project we've been working on is to try to do this kind of visualization collaboratively, and not just to do it with a scale model of the city, which you're seeing here as grayscale buildings, but to do it with a lot of virtual data that is geo-referenced, geo-tracked, being provided along with the actual urban model. And so in this case, you're seeing these records, each represented as a little card, and these in fact are records of calls to the New York City 311 number. That is the number you call in New York if you have a non-emergency problem, like a pothole or a noise, or you see a big rat running in the street. All these kinds of things you're not supposed to call the police about, but the city wants to know, and people will take the call, enter information into a database, and then that information gets acted on. And so this is one example of what are basically hundreds of databases that are out there in New York City open data, all accessible literally to anyone who wants them. And so what we're doing in this project is we're trying to take this model of the city and put live data from a variety of sources, including New York City open data, in it. So let me show you what this looks like. Here we are looking around. You're seeing those New York City open data 301 calls. There are tweets that are coming up over there. You know, I'm going to make this small again. I forgot to do that. Should run a little bit better then. And now we're able to go and one of those 311 call records, grab hold of it, scroll through it, grab hold of one of the tweets, for example. And all of these are live literally when that laser pointer got aimed at the ground. As soon as you saw those records popping up, that was after we went out to the different databases, Twitter and New York City Open Data in this case, and actually got those chunks of data. So this is VR. Let me show you what AR looks like. And so what we're seeing over here is a video see-through AR version of this system. In this case, running on a Vive Pro, which has a stereo pair of relatively low-res VGA cameras. And what our user is going to do is look around and then show you an example of the kind of thing we could do to collaborate with somebody else. And in this case, with all these little records, the idea is that there may be interesting places where you can see records that relate to each other. And then what we're going to do when we see that is we're going to let the user grab hold of them and essentially make cloned copies of them on a big bulletin board that's shared with the other users that are in the environment. You can see a bit of that bulletin board, that big gray kind of triangle-y looking thing on the right. And then as we play the video, you'll see that that actually is going to enable us to put copies of these records on it. So let me start the video up over here. Now we're looking around, we're seeing tweets, we have Yelp records, more of those 311 calls. We can grab hold of a restaurant review, for example, clone that on that board over there. Here's another restaurant. Maybe this is related, so we kind of put it close to it. You can grab hold of them, move it around the same way you would move a Post-it note, let's say, on a regular bulletin board. Meanwhile, our other user off in the distance is seeing copies of these things. And we can put all of these together, make hypotheses about how they might relate with each other. Perhaps it turns out that you're seeing reports of people complaining about noise, and maybe you're looking at a restaurant whose information is nearby, and you're seeing reviews about how they have really good bands playing there. So maybe the noise has something to do with the bands, for example. There's lots of places in which you can look at different kinds of information and then be able to make these kinds of hypotheses that can make more sense when you're seeing them all together live and in context of this immersive environment. So let me get past that. Let me talk about one more application that we've worked on. And now we're going to go to something that currently is not collaborative. And this is being done in a medical domain. We've been working for around 2 years now with colleagues in the medical school on a project that is actually being used live with patients for the past year, in which we're trying to make it possible for physicians performing what are called vascular interventions, which they're snaking catheters through the veins of patients and then threading wires through those catheters to be able to do a variety of things that are diagnostic and in some cases actually perform procedures that are designed to go and put, for example, certain kinds of apparatus in place in the patient's body. And so what we've been concentrating on is making it possible for the physicians we're working with to be able to be assisted by seeing representations of patient-specific anatomy as they're actually performing the tasks. And so what you're seeing on the left over there is a representation, a model, in fact, made through medical imagery of a particular patient's heart that happens to have a defect in it, and that is being used to guide the physician as they are moving their catheter through the patient's body. For the physician to see what they're doing, they enter basically in one place, one part of the patient's body where it's relatively easy to get access, where the veins are bigger, and then they often are moving their catheter and the wire through it to other parts of the body, which are not open in this minimally invasive surgery, meaning they don't have to actually look at the patient while they do this, but instead they're looking at live data coming in through, for example, fluoroscopy, which is live X-ray, and a bunch of other kinds of data that they're seeing typically on a big screen, which you can actually see at the upper top of the right-hand view of the head of one of the people participating in a procedure. Now, if we did this with a conventional HoloLens kind of interface, this being done with a HoloLens, if you wanted to rotate or scale or translate something, you would do the classic HoloLens air tap, necessitating you have your hand up in the air and then move it around to be able to go and grab something to rotate it or scale it, translate it, etc. Now, in these tasks, the physician's hands are busy. Typically, their non-dominant hand is holding the catheter or the end of the catheter. Their dominant hand is threading the wire through the catheter. And if they want to do something with the interaction, they're going to have to let go typically of the wire, interact using that classic HoloLens air tap, and then grab hold of the wire again. And so what we wanted to do is to make it possible for the physicians not to have to do that. In fact, the first version of our system was a rather classic HoloLens interface, and we developed the hands-free system I'm going to tell you about in response to requests by the physicians for them not to have to go and stop doing what they're doing when they want to go and actually interact with the system. And so these are three views of what's happening with our hands-free interface. If you look at the bottom, you'll see three views of this particular heart model. You'll notice it's rotating about an axis. It's roughly perpendicular to the ground, rotating a kind of counterclockwise around that axis. And to be able to do that, what's happening is the patient, rather the physician's head, the user's head, is moving very slightly to be able to actually control what's going on. The person using the system is going to be using voice to express the modality they want to enter, rotating or scaling or translating or changing transparency, for example. And then how they do it, the amount they do it, is being done with head motion. And so in this case, if you look at the three images of the person's head at the top, they might look at first like they're the same. They're actually a little bit different. And so if you notice what in your view is the left side of the patient's head, actually, excuse me, of the physician's head, actually her right-hand side, you'll notice a little bit of her hair that you see on her right gets thinner and thinner because she's actually turning her head a little bit towards the right. And that motion towards the right is controlling the speed with which and the axis about which that heart is rotating. So very, very small motions in this case, what we call first order control, means that as you deviate your head a little bit to the right of the center of looking at that heart model, you're determining the speed with which the rotation occurs, and the direction in which you look away from the center is going to determine the axis about which the rotation occurs. To give you another example here, in this case, scaling, when our user looks a little bit to the left, this is going to scale this model down. When they look a little bit to the right, it's going to scale it up. And for translating, because sometimes we want to grab hold of a model and move it a little bit to the left or right or above or below or a little bit further forward or backward, in this case, you get into this translation mode, and then the model gets essentially attached to your head, and you can basically look, as in not eye tracking, but in head pose, and have the model actually follow it and then let go of it. So let me show you what this looks like. I'm going to show you a little video. Again, I'm going to go and make it a little bit smaller. There is some audio here. And so what I'm going to do is I'm going to take off my headset and microphone, unplug it, and that unfortunately is the only way using the Zoom system right now to be able to allow you to actually hear the audio of the person using the system. And what you're going to see actually is a trial from a test run of a study that we're doing, in which you're going to see not just a single heart model, but a destination heart model that needs to be matched, in which the size and the orientation and the position, as well as also the transparency, is going to be controlled using this hands-free head orientation-based interface. So let me unplug right now to actually start using the speakers built into my laptop. Give me a couple of seconds to make sure that I have the audio up. Seems to need that. And now I think if I play this, you'll actually be able to see it and hear it. So let's try.
Train.
So now you see that transparent
Hands-free.
version of the heart
Move.
as the destination. So now it's being moved into place.
Stop.
In this case with zeroth
Rotate.
order control. Now you're seeing first order control, speed control of the rotating heart.
Stop.
Slightly different axis
Scale.
being chosen. Now it's being scaled to be bigger.
Stop. Transparent.
Now it's having its transparency changed. And in this particular case for the study, we're basically allowing a certain amount of slop, because in fact in this particular task, the physicians using it have made it clear that they don't need things to be exactly at a particular orientation, but a good enough orientation for the work that they're actually doing. And again, the idea is to have them be able to do this without having to use their hands, which means stopping what they're actually doing. I'm going to try to plug back in again. See if it's going to let me do that. And yes, I will do hardware. And I think I might need to.
Nope.
No, my
You're
volume
loud
looks like
and
it's
clear.
good.
Beautiful.
Okay, good. I can move that out of the way. And I think at this point, I am going to get ready to stop. So I've, just to review, talked a bit about work that we've done in a variety of different task domains, developing interaction techniques and visualization techniques for AR and VR. And what I want to do next is to mention before I stop, many of the things that you saw were done with something we call the Mercury messaging framework. This is an open source Unity implementation that makes it possible for Unity programmers to be able to establish relationships between different parts of a scene graph, ones that are not the really easy up and down the scene hierarchy kinds of relationships, but ones that essentially cut across arbitrary places in the scene graph, to do this in a standardized way rather than writing custom code, and to do it in ways that not only work on a single machine, but let you talk between scene graphs on multiple machines without having to worry about all the low-level networking. So we have released this open source. You can see the URL at the top over there. We encourage you, if you're interested, to actually use it and maybe even help us further develop it. So at this point, I'm going to stop, acknowledge the many colleagues and funding agencies that have made the work that I've talked about possible, and hopefully have a little time to answer questions. Thank you.
That was great, Steve. That was really, really good. Can you hear me okay?
Yes, I can.
Super. It's always interesting to see a surgery happening in a computer science lab, you know. It's
Mhm.
a little bit of
Well,
cognitive noise there.
that's actually not those demos were being done in our lab, but the actual procedures are in fact done in a hospital in an appropriate surgically correct environment.
Exactly.
Although often, especially when they're going into the patient's head, the patient will actually be awake, um, which is important in case something goes wrong.
Yeah. I'd like to ask anybody who has any questions to put those into the chat window. You can address them to me or to Stephen. We can go through those. But first,
Let's see if I can see them. How do I see the chat window?
well, in your control panel, you'll see that in the
Okay.
bottommost section, there's a little
Ah, it says chat and looks like I need to click on something. There we go. Now I can see it. Okay.
So let me start by asking a question. It's clear from your talk that you've exposed um, hundreds, if not thousands, of people to this particular to different concepts. And I wondered if you could share a little bit about um, what kind of data can you collect, like at a SIGGRAPH, or where you had hundreds of people coming in for that remote expert visualization with the AR and VR combined. Can you use that at all for feedback, and how does that work? It's fantastic to be able to
Okay.
plan 5 minutes. People come in
Yes.
to learn how to do it and leave. Wow, that's so quick.
Okay, so it turns out if I had wanted to, we could actually have filed an IRB protocol as a government-funded institution. Columbia is obligated to properly obey the requirements that are placed on people doing human subject experiments. So I could have decided to fire a protocol. I think I would have been able to get away with relatively simple consenting process. But that would have taken some time. I would have had to have given people the form to fill out. They would have to agree to actually participate and to have me use their data. And we had 5 minutes total. And I did not want to do that because some people don't like that.
Sure.
So
Okay.
what we did is, what we have done for these things, not that particular one that I showed you, but an earlier experiment done in fact with pieces of that turboprop engine domain, we actually did controlled experiments that were done with IRB protocols, with people spending a whole lot more than 5 minutes learning how to use the system and trying it with a variety of different versions. What I could get out of the SIGGRAPH experience, however, although I'm not formally collecting data, is if people are having a lot of difficulty, I can try to understand, my students and I can try to understand why that is happening, for example. If people are doing well, we can hopefully benefit from knowing that they are doing well.
Right.
But from my standpoint, we can always do better, right? We're not at the point right now in which we're actually being optimal. But it was most important to me, since I didn't control the people who were using the system. I don't know about things like, do they have stereo vision? A number of people do not. Are they colorblind? A number of, depending upon the demographic, and this is mostly male, you'll get a very high single-digit percentage of people who are have some kind of color vision deficiency.
Okay.
So these are all things that when we do studies in our lab, we actually look at, because they can sometimes explain why someone might not be able to do something really well. We do tests, for example, of mental rotation to get a sense of how good people's spatial abilities are. All those things take time, and they're not things that I wanted to actually do in the SIGGRAPH environment.
Okay.
So
Great.
what we got was a lot of informal feedback. And one thing we find is, and it's really in some sense kind of shocking, there's a lot of very bright people at SIGGRAPH, but there are a number of people who have real difficulty understanding what to other people is trivial. There are people who, when you try to explain, there's a cross the cross section of the physical gear is a square. The axle is a square. There's only 4 ways the gear can line up and actually get onto the axle. There are people who, having had what we think are pretty good explanations of that, will sit there and try to force the gear on in a way that isn't properly aligned.
We have a couple of other questions.
Anyway, yes, please ask
I
away.
So one of the questions is spatial dimensional accuracy necessary for that hands-free control in the vascular intervention demo? Is spatial dimension accuracy necessary?
Okay. The answer is, depending on what you mean by accurate, in that particular task, the physicians we're working with have told us, it doesn't have to be, rotated 44.3 degrees about the vertical axis, for example. There's a fair amount of slop that they have. Now, if they're looking at a really wrong view, that's no good. So they do need to be able to get it to a good enough view, harking back to my discussion before of what good enough meant. Now, that said, the folks who do that kind of stuff, the people who are doing these vascular interventions, are working typically and not with really nice 3D models correctly oriented. They're working with fluoroscopy, which is basically live X-ray. And the C-arm system that the patient is lying on the table of has 2 of these things. And those folks, people who do this for a living, do it because they have learned how to, and they have the innate ability to look at 2 different views, shot fluoroscopically and live, and figure out in their brain in 3D what's actually happening. There's a lot of people who can't do that, and those people do not end up going into that part of medicine. The same with some parts where you need to be able to saw through things that are really thick and have a lot of strength. These people need to be able to go and do this stuff in their heads.
Yeah, and this is
so
really,
this is actually helping.
Yeah, it's also related a little bit to the next question, which has to do with accommodation and divergence conflict.
Yes.
So again, it's a question, like you were just saying, some people can align spatially these 3D models from 2 different directions. Given the hardware we have today, like HoloLens in the AR case,
yes.
Do you consider that the accommodation divergence conflict is a problem for the tasks like the ones you have discussed? Do the devices we have present a limitation? Can they be used in production environments?
I think the answer is it depends. There are folks like me who go to stereo movies, for example, 3D movies, and I have a wonderful time and I enjoy it. And even though I have colleagues who will tell me if I actually got a vision test after spending a couple of hours looking at this version's accommodation mismatched image in which things are coming a bit out of the screen and going into the screen, and yet they're all focused on the screen, that I would not do as well on that vision test. For a while after experiencing this. But I enjoy going to 3D movies. My wife, on the other hand, gets a headache. And I actually have to make her glasses by taking 2 pairs of glasses and making 1 pair that has left for the left and right eyes, and the other one has right. So she sees a somewhat dimmer version of the non-3D movie at the great premium price of the 3D version if she wants to sit with me. So for many tasks, there are some people who don't have a problem, at least they don't feel they have a problem, others who really just can't do it well and get a headache, and other people who I think one could argue maybe they're not going to perform quite as well as if they really had matched versions in accommodation.
Right.
So I think that we clearly can do better. There are some interesting potential technologies that can do this. If we really had a light field display, a true perfect light field display, the things that are virtual that we see would really emanate light in a way that the real things that they're supposed to be versions of either reflect, transmit, or maybe also emanate light.
Right.
So it should be visually indistinguishable. Right now, we cannot do that with what is currently on the market. I think we are all waiting for what is certainly not physically impossible, which will be really good light field displays. It will be wide field of view and inexpensive and lightweight and all the other wonderful things that we'd like them to be.
If
But
we
for
have
right
patience
now, I think there
and
are
a lot of
many
money.
tasks. Yeah. Well, hopefully they should not cost a lot of money, because if they're made in enough quantity and they don't involve either really expensive magic or stuff like gold, for example, in large quantity that will probably never ever be cheap because alchemy doesn't quite work. Um, as long as it's something that can be done with more classical technology or not so classical technology, when you make enough of it, it can be inexpensive enough. And so
Well,
I think we're all trusting that
yeah,
will happen in the future. I
let's
can't tell you when, however.
no. In fact, this leads us a little bit to the next question and
Mhm.
folding in, the recent experiences with Meta and everything. Somebody
Yeah.
asks, what is the minimum viable AR display for enterprise tasks? I don't know about, I think that we would need to better understand what the use cases are, because it seems
Right.
like it's all down to the use case.
Absolutely. If the task is, for example, order picking, and the three-dimensionality of it isn't all that important, you don't really necessarily need to see it in stereo. It'd be something you might have done in the past with a clipboard and maybe more recently with an iPad. And now you can maybe have a small, lightweight, perhaps monocular head-worn display on. That means you don't have to have your hands full of clipboard and stylus, and instead can actually or iPad and stylus, and can instead actually, pick things up with both hands, and be guided, from one aisle to another in the most expeditious path to go and get things. That's wonderful. And it's not clear that you need stereoscopic displays for that.
Mhm.
On the other hand, if it is a complex 3D task in medicine, certain kinds of complex 3D tasks in trying to fix stuff, just threading a needle, for example, if you're
Right.
doing stuff where you need to be guided as to which of a set of needles need to be threaded, let's say, in perhaps some kind of big milling or sewing or knitting machine. Then you probably will need stereo, and depending upon the domain, you might need very wide field, perhaps because the system needs to warn you about stuff that's
Right.
coming in to the left or right or above or below. So as you're right, it depends on the task, and the MVP in terms of both hardware and software is going to be very dependent.
So, recently you've done a lot of work in both VR and AR, and recently it's come up a couple of times. People asking about, do we know that there's a lot of motion sickness and disorientation in VR, and you spoke about it with the theater and the 3D vision and everything like that. Is there as much, or have you encountered any of this kind of motion sickness or cyber sickness with AR displays?
Okay, well, first I can say that the nice thing about AR, especially optical see-through AR, is that the real world that you see is reaching you at literally light speed. And that means that the matching between what your eyes see, what your ears hear, and what your inner ear tells you is about as good as it gets. When you're
It's what you
doing video
expect,
see-through,
especially.
it's what you expect, and you well, obviously people can get motion sick on a real roller coaster with their real eyes looking only at real stuff. Those are extreme cases. So for most things that you would do where you're seeing mostly the real world being seen correctly with zero latency, that should not be a problem. If you think about doing a thought experiment, if I put a optical see-through AR head-worn display on you, and I have a couple of pixels worth of virtual stuff, and they move around in a kind of jittery, annoying way, imagine them being a little bit like, gnats or little tiny flies moving in your environment. No one gets motion sick watching you might get, physically sick
Annoyed.
watching a bunch of little flies buzzing around near you, but you're not going to get any kind of motion sickness from that.
Yeah, I have not
On the other
experienced
hand,
any or
a
heard people.
lot of virtual stuff that is not properly moving relative to what your inner ear
Yeah.
tells you is going to cause the problem.
And you know, 10
so,
years ago, an AR experience would be very jittery. Remember, you'd like hold up your smartphone and the thing would just like
right.
jump around. I love this jumping buildings kind of stuff. It's a
Right.
problem. But I don't see that. I mean, it's just really,
That's
really,
getting better, but if most of what I see is tracked smoothly but not accurately, and as I move my head, they lag a bit and then they
yes.
catch up, and they're really wide field of view, which is, in a naive way, because you can get people feeling VR sick with a very small field of view if you actually really design it right. But in general, it's easier, or wrong, as the case may be, it's easier to do this with situations in which there's a very wide field of view. And so again, in AR, where the more it is that you see that is correctly zero latency, matched, moving the way that your head is moving, the less likely you are to get that kind of uncomfortable. On the other hand, when it is VR and there's that mismatch between what your inner ear is telling you and what your eyes typically are telling you, that does cause a problem. We actually, in my lab, did a project 3 years ago. We had a paper at the 3DOI conference in which we were doing a system in which, in VR, we had people moving with joysticks to translate and rotate, in addition to moving their head around a little bit, but they were trying to really like walk forward while they were seated. And in that work, we basically controlled things so that as you had a mismatch between inner ear and eyes, we very slowly decreased your field of view, the VR field of view, in a way in which, instead of being a crisp kind of cutout, we used a sort of feathered edge around that decreasing field of view. We did it very slowly. We didn't do it too much. Where how slow and how much was based on doing pilot studies with people. And we were able to show in an experiment that when we actually did this, that people who didn't know what we were doing actually reported less VR sickness than people who were being exposed to the normal full field of view, and as well also didn't know we were doing it. So you can see an extreme example of this in experiences like Google Earth VR, which is a really, really compelling system. But they, by default, put on this kind of field of view restriction in a very extreme way when you're in a situation in which, for example, you're looking at directly at the Earth, you're rotating the Earth beneath you, and you're feeling, your inner ears are telling you that you're sitting still, your head isn't moving, and yet your field of view is telling you that you're rotating. And by very drastically cutting down your field of view, they keep people from getting sick. You can actually turn off this default technique that they're using, and when you turn it off, most people will turn it back on again very, very quickly, or else just stop using the system. But
Hey,
in that work, we were actually trying to make people not know we were doing it.
tricky. We are past 1 hour. It's just always super interesting to hear the things that you are doing and have done, and your insights are extremely valuable. Steve, thank you so much for participating in this webinar. And I'd encourage all of those who are attending and who have follow-up questions to reach out to Steve via the web, and his email is pretty easy to find. So with that, I will end this webinar and thank everybody for their participation.
Okay,
Bye-bye.
goodbye.